Welcome everyone to our next lunchtime seminar. And today's seminar guest is Dr. Rehan Bhatti, who will be talking about the light-driven actuation in ultra-dry chain oriented polymers. Dr. Rehan Bhatti is an ambitious researcher in the field of advanced materials science, renowned for his pioneering work on stimuli responsive ultra-stiff polymer actuators. Dr. Bhatti experience extends across a broad spectrum of areas, including functional materials, polymer processing, composite manufacturing, and technical textiles. Dr. Bhatti is also currently holding a position as a senior lecturer at the University of West of England. Committed to innovation in teaching and research. His academic industrial expertise spans over a decade. Dr. Bhatti has made significant contributions to the literature, publishing high-impact journal papers, and serving as a reviewer for the top-tier journals, reflecting on his standing in the academic community. I will hand over now to Dr. Rehan.
Thank you, Julia. Thank you very much for providing me an opportunity to present my research work in front of you. I would like to start with a brief introduction of myself. Well, I did my bachelor's in textile engineering, specializing in yarn manufacturing, and soon after completing my bachelor's, I joined a well-known industry back in my country, and I got a 6.5 year experience of fiber processing, spanning from natural, man-made, and synthetic fibers. Then I did my master's in textile engineering, specializing in technical and functional textiles and composite materials from the same university. I spent 3.5 years working as a lecturer in one of the prestigious university back in Pakistan in the Department of Textile Engineering. Then I came to UK to pursue higher education. I did my PhD in light-driven actuation in ultra-dry chain-oriented polymers from Queen Mary University of London. I did 1 year postdoc in association with companies like the ESA, it's a defense institution, and BSTL and the University of Warwick. We developed transparent armor-based high-strength polyethylene films. Alongside that, I was working at Queen Mary University of London as a teaching fellow in the School of Engineering and Materials Science. Recently, I joined UV in the Product Design Engineering Department as senior lecturer. Let's start with my topic for today's presentation. I'm going to highlight some of my research works, and if I got some time, I will also talk about some of my future work, our ongoing work. Today, I'm going to talk about light-driven actuation in ultra-dry chain-oriented polymers. Well, I would like to start with a famous quote of Richard Feynman, which is a famous theoretical physicist back in 1960s. He also was awarded a Nobel Prize on his quantum mechanics theory. He proposed that some of the materials can be actuated using external stimuli such as electricity, magnetism, and most interestingly, light. He proposed that at that moment, he was not sure what would happen, what kind of machines we can produce. But he was very much sure about that when we were able to see things or understand things at a molecular level, there will be enormous possibilities of creating substances that can be controlled by external stimuli. Let's start from the ground of that concept of Richard Feynman. I would like to highlight a few stimuli found in the nature and also that we can engineer by ourselves. The most famous are light, heat, moisture, and also we can say electricity, magnetism, and chemicals. These are the stimuli that can initiate some kind of response within a material. If we talk about actuators out there, which can be controlled by external stimuli, we can classify them majorly in two broader categories. One is organic, comprising polymers and elastomers, and the other class, which can be characterized as inorganic, comprising metals and ceramics. And there is a combination of these two, organic and inorganic, which we can classify as CNT fibers and yarns. But my work is basically surrounding around polymers and some of the composite materials. So I will talk about basically about these categories only. The whole actuator the actuators class is basically derived from the concept was coming from the natural muscle of the human body that is being controlled and actuated, used to perform different tasks of our body. So the problem with the existing actuator, although there are so many actuators out there at the moment, but the problem with the actuators is are that they can produce actuations which cannot be reverted back. I mean to say, these are not reversible, or if they are reversible, they lose some kind of properties when getting back to their original position. Or they are very small, very slow in processing, like they are not rapid, and most of them are not recyclable. That, for example, the materials, the processes that we're using, these are not reproducible or recyclable. What we need are what are the best possible characteristic of a good actuator is that the response should be rapid. It should be reversible so that we can use it again and again. And also it should be simple, easily available, and can be recycled, can be used again and again. These are the characteristics that should be there for an ideal actuator. On the basis of the existing theory, we found out that there is a scope to produce an actuator which is ideally an ancillary-free actuators, because the actuators like SMA are CNT-based actuators, are ceramics-based actuators. These are very good in terms of mechanical deformation, but they are very complex. They require so much ancillaries that make them not so ideal for being used in some of the applications. So there is a scope for ancillary-free actuators. And also, as I mentioned in the previous slide, the response time and reversibility is the crucial parameters for an ideal actuators. But most of the actuators either are not reversible on their own. We require another external factor to make them useful again, or the response time is very slow. What we can also do is that we can think about a material which is lightweight and flexible, because the materials like SMA and CNT, they have very high densities, making them very heavy. Also, we can think about specific actuation stress, because the existing actuators are either focusing on the actuation strains, getting more extension in terms of actuation, not focusing on the actuation stress. But if some of them, like for example hydrogel, but if some of them are focusing on actuation stress like ceramics and SMA, they are not producing actuation stress in terms of specific strength, because they are heavy materials. So there is a lot of scope to consider when we have an outlook of the existing actuator materials. And on the basis of that, we established a chart to get a clear picture of what we have at the moment. If you see on this chart, we can say that the actuators families can be classified in terms of in different materials. For example, metals, ceramics, composites, and soft polymers actuators. And in particular, if we think about the polymers, all of the polymers actuators out there are soft polymers. They are focusing more on actuation strains rather on actuation stress, or they are using some kind of medium. For example, they need a solution to be activated and they cannot be used on their own. So we thought that there is a place for a polymer actuators which is not soft but stiff, but also keeping its flexibility. And in order to get rid of the ancillaries involved in SME and ceramics actuators, we need to address them remotely. And there should be possibilities that these are industry viable, these are recyclable materials, are commercially available materials which are not very costly, easily accessible and usable. So all of these became the basis of our work of creating stiff polymer actuators. So move on to the recipe of what we were going to create, what we wanted to create. It comprises basically of three ingredients that we can say. The first and the foremost is the light, because we wanted to actuate material remotely, not creating any link with that, and what would be the best source other than the light. And light is also very much interesting because it can be modulated in terms of wavelength, intensity, and polarization direction. And light is easily available. We can even actuate materials using sunlight, for example. And using light as a stimulus provides an advantage of creating an ancillary-free actuator. The second part of our recipe is to utilize a material as a substrate in which we can use to actuate something. And we wanted to create a lightweight and flexible material, and polyethylene comes into our mind, which is easily available. It's commercially very cheap material, and it's lightweight. And the density of the polyethylene is around 2.95, less than 1, making it a great advantage over other materials like SMA and ceramic materials, because the density of those materials are very much high as compared to polyethylene. Polyethylene is an interesting material because if we see on the molecular level of this material can be attenuated in terms of chain orientation direction. If we draw these materials, we can have a very high stiff material with a very good mechanical properties like Young's modulus. And also the most important property that we are going to use is the negative coefficient of thermal expansion. So when we orient polyethylene, the chains are oriented, crystallinity of the materials is increasing, and material is experiencing a negative coefficient of thermal expansion. That means if the material is being heated, rather expanding, these materials will contract. That will be very much helpful. And polyethylene can accommodate a lot of materials. We can introduce a photoresponsive additive within polyethylene, and also it can be the polyethylene can be processed by different processing routes. For example, it can be melt spun, it can be solution cast, it can be gel casted. So we can use polyethylene, we can produce polyethylene in a different way. The third but not the least constituent of our work was choosing a right photoresponsive agent. And we found that BZT is commercially inexpensive material, very cheap material, and it's being used as a UV absorber in polyolefins and plastics like PVC to protect them from harmful UV rays, and which become the ideal candidate for our work, because we wanted to use light as a stimuli agent. And what could be the best possible material other than the BZT, which actually absorb harmful UV rays and convert them into a heat which can be used to actuate the substrate. The thing that we need to consider over here is that BZT is compatible with polyethylene. And thanks to polyethylene refractive index, which is almost identical to BZT, and this actually these two materials complement with each other, because adding BZT within the polyethylene actually fills the micro voids that created when we draw polyethylene. And with the removal of these micro voids, the transparency of the polyethylene has been increased, which is also a benefit that we need, because if we are going to illuminate something with the light should be able to pass through it, and if the material is transparent within the visible region, that would be ideal for this case. And using BZT polyethylene with the high Young's modulus and the light as a remotely addressable material, we were aiming to create a specific actuation stress, because an oriented polyethylene material can generate a very high specific actuation stress because of its being lightweight. Moving forward to not talk about, it will be not good to talk about other photoresponsive materials that can be utilized. So at that time when we were doing our research, the two materials were very, basically it's a combination of two materials, liquid crystals and azobenzenes. The combination of these two materials, azobenzene is also a photoresponsive agent. It absorbs light and changes its shape from a trans state to a cis state, and that was being used to create some of the deformations, mechanical deformations in polymer materials. But the problem with these materials is that we need to synthesize these materials within the polymers, and this requires long aliphatic chains to be characterized, because this is dichroic in nature, which means that we need to, these materials should be aligned with the polymeric chains. If these are not aligned with the polymeric chains, they cannot do mechanical deformations in that range, and we need to use a polarized light. For example, if we wanted to see these kinds of deformations within the materials should be aligned within the polymeric chains. And also this synthesis process, this complexity of the material makes it very hard to be utilized. We wanted to keep things very simple, that actuators can be produced in a very simple way with the existing with the industry viable route. Does not require so much expertise. The problem with the azobenzene is that it is good with the soft materials like liquid crystals and like polymers like hydrogels, in which the materials are soft. But since we are aiming to create actuation in a stiff polymer actuators, the trans to cis transformation might not be well with the stiff polymers, although scientists believe that it is possible, and that the stiff polymer actuation is basically caused by the transformation of trans to cis state. But that would not be the case. And one of our research group was working on this state and found that this is not because of the isomerization of the isobenzene, but also because of the photothermal generation of heat when the trans state is being converted into cis state. So moving forward to that, we believe that benzotriazole BZT is an ideal material to be used as a photoresponsive agent within polyethylene. So in the following slides, I will talk about some of our research work, starting with the high density polyethylene, because high density polyethylene can be this process is very simple. We can produce high density polyethylene films or filaments or fibers using melt process, which is a very simple process. So we started with creating high density polyethylene embedded with the BZT. We used twin screw extruders to create pellets, and then a single screw extruder to create films. These films contains benzotriazole in different concentration because we wanted to characterize the different properties of the materials to get the highest possible actuation stress at that time. So what is happening when we illuminate the benzotriazole containing polyethylene films with the UV light? I wanted to mention that the benzotriazole absorb maximum absorption of the light at a 365 nanometer of wavelength of UV light. So we use a light with that wavelength. And the electromagnetic waves are being absorbed by the benzotriazole, and in return, it generates phonons, which is a vibrational heat energy. This vibrational heat energy is absorbed by the oriented polymer chains because the polyethylene is being oriented. The chains are oriented in a certain directions, and so anisotropic properties are there. So when these phonons are absorbed by the polyethylene chains, these chains tends to contract, rather expand. And if we clamp these films in a tensile tester, restraining it to contract, the response will be in terms of actuation stress. So we devised a simple experiment of tensile relaxation. So in that experiment, the strain is kept at a constant level. And because of the viscoelastic nature of polyethylene, the material tends to relax in terms of tensile stress. But when these films containing BZT is illuminated with UV light, they respond in terms of actuation stress upon UV radiation. As you can observe over here, whenever the light is illuminated, we try to illuminate the polyethylene films with an interval of 10 seconds. So as soon as the light is being illuminated, there is a short peak observed, which was an actuation stress. And as you can see, it is very rapid, it is reversible, and it can be generated as long as we want it. We tried different concentration of BZT within polyethylene, and for each concentration, the response was there, even at a very small concentration of 1% of BZT. And also we can see over here that as the concentration of BZT is increased, the response is also increased. But the problem with the higher concentration was that we were unable to eliminate the whole film, and also with the increase in the concentration of BZT, since the light photons are being absorbed by the BZT, if more BZT is present within the films, there will be more absorption, and technically there will be a black region behind the film through thickness. That means whether the light does not reach to that point because of the high film thickness, or maybe there is a higher concentration of BZT that restricts the materials to get to the later end of the film. That means there is a thermal gradient generated within the films. That gives us a base to think about that we should create a film that that should be thinner, because at a thinner film level, maybe we will be able to eliminate the thermal gradient and can generate a higher actuation stress. But the problem with the HDP is that we cannot draw the films from a certain draw ratio. We tried up to 20 draw ratio, but at that draw ratios, the microvoids were generated, especially in the vertical direction, as compared to the chain orientation direction, which in turn reduces the transparency of the film and also the strength of the film. So we thought of using another material, which is ultra-high molecular weight polyethylene with a high molecular weight, but the process is different. It is not being processed by the melt processing because of the high molecular weight. We used a gel casting process in which ultra-high molecular weight polyethylene powder is being mixed with xylene, a solvent, and then adding B-13 to that, and then gel casted it in a sheet, dry it, and then get the sheets and then draw it later on to get a high draw ratio. With using ultra high molecular weight polyethylene, we were able to create different draw ratios of 40, 60, and 80. And we were aiming to get a higher actuation stress, which was actually be the case, and we successfully get a higher actuation stress by just increasing the draw ratios, just getting the thickness of the film to the lower side. But as we were anticipating that increasing the draw ratio will increase the actuation stress, to our surprise, we got a plateau. Like we did not get a regular steep curve. We get an optimum value. At a draw ratio of 60, we get the maximum possible actuation stress with these films. And as we increase the draw ratio, the actuation stress was decreased, which was a surprise for us at that moment. And not to be mentioned, it's important to mention over here that the actuation stress is generated because of the heat generated by the BZT after absorbing UV light, converted it into heat energy, and we can see that the heat signatures were there. These are the infrared images of the films, and we can see as soon as the light is turned on, and the heat, the film samples are being heated up, and this heat is actually causing the materials to contract, but we are limiting the contraction by holding the films from both ends, thus increasing the actuation stress, and that we can record. So successfully, we produce a very high specific actuation stress thanks to the low density of polyethylene. We managed to get up to 70 megapascal of actuation stress using BZT, polyethylene, and light. And as you can see, we are able to create a stiff polymer actuators with a very high specific actuation stress. But the question remains there that we were clueless at that moment why the actuation stress gets down at a higher draw ratio. I would like to mention over here that using the maximum draw ratio for any polymer material depends on the molecular weight of the polymer, the concentration of the polymers within the solution, and also on the processing route. So the maximum possible draw ratio with our parameters using ultra-high molecular polyethylene was around 100. So we thought that 80 is very much closer to the maximum attainable draw ratio. And when we are reaching to the maximum attainable draw ratio, although the Young's modulus is on the higher side, but the negative coefficient of thermal expansion is on the lower side. So we are achieving a higher Young's modulus, but we are also getting a lower coefficient of thermal expansion, which we were thinking at that point is the base of getting actuation stress. But since these are counteracting each other, so we thought that there should be an optimum value which we observe at a draw ratio of 60. But to analyze it further, what is the reason behind that? We advised a semi-empirical model. We theoretically analyze what is happening in between at a molecular scale at a polymer level that this happened. So let's consider different types of films in terms of thickness and in terms of draw ratio. So if we consider, let's say it's a draw ratio of 20, 40, 60, and 80, or you can also say different film thicknesses like 30, like 10 and like maybe 8 or 5. These are the molecular arrays within the polymer or the polymeric chains, and we have a BZT in there. When there is when the film thickness is higher, the photons is unable to reach to the back end of the film, leaving it in the dark, and does not harness the true potential of the BZT within the film, because the BZT materials present at the back of this film are not being utilized. So we are not getting an actuation stress that we had to get because of the thermal gradient generated. And as soon as we're reducing the film thickness, the actuation stress is increasing. And at some point we reach to an optimum level where all of the BZT within the film are being utilized, converting into an actuation stress, and there is no thermal gradient in theory. But as soon as we move forward, making it much thinner at a higher draw ratio, the light passes through the material without being utilized. Like, for example, the film, the photon energy is not being utilized properly. So so there should be a balance between all these parameters, like the concentration of BZT, like the light intensity, the film thickness, and also the Young's modulus and Young modulus of polyethylene and coefficient of thermal expansion. So at that moment, we realized that we are not considering a very important factor, which is delta T. Delta T is the difference of temperature between the illuminating and non-illuminating state of the polymers. So by considering that point, we thought that because of the counter effect of Young's modulus and negative coefficient of thermal expansion of polyethylenes, the effect of draw ratio on the actuation stress is very minimal, and it's around it's like a straight line. But the effect of delta T is there. So higher the temperature difference within the polymeric film because of the heat generated creates actually the actuation stress. So we got these values with respect to delta T, and we devised this equation that actually fits very well with the actual results that we got to, and it coincides with the theoretical results. So we modified the initial chart of our actuators, but in this chart you are only seeing the polymers. After our work, we were able to generate polymer actuators that range from a very high actuation strain to very high actuation stress. And depending on the usage, depending on the applications, which we can utilize any kind of polymeric materials, which was quite astonishing. So moving forward, based on our research work, we found out that polyethylene has not having a very high melting temperature. So there is a term used, alpha relaxation temperature. So we see that we can, if we increase the concentration of BZT, there will be an increase in the actuation stress. One must thought that why we cannot go further from 5% of BZT. So increasing the BZT, whether it generate the thermal gradient, or it can also increase the temperature within the polymeric film, and it can go beyond the alpha relaxation temperature. Beyond that, the polymer chains starts to relax. That means they are not going to contract as the temperature is increasing, and if the temperature goes much higher, the chains can also be melted. So it limit in terms of polyethylene, but that means we can use other materials, because we saw that lambda, like the draw ratio, is not playing a very significant role here. So we can use polymeric materials with high temperature resistant properties, such as polyamide, polyester, that can resist heat much better as compared to polyethylene, and at a lower draw ratio. So we can explore that thing. As I mentioned before, because we are using ultraviolet light to get this actuation process, and the natural light contains ultraviolet ranging from 280 to 420 to 380 nanometer. So we can use natural light and modulate that to create this actuation process, and this gives us an opportunity to think about the application perspective. For example, we can use in normal clothing to create contraction depending on the temperature rising or lowering, and also in the curtains in the house to get more light or less light depending on the situation and the outside. And also we can get an inspiration from the design, because in the nature design plays an important role. It creates sometimes a very high quality functional structures without having a need of very high-end material that we need to produce. So if we think about some clever designs, such as fish fins, such as wheat-ons, or some of the insects' wings, they have anti-reflecting or self-cleaning properties just because of the design. So we can think about some things like that to create very good materials. Also, we can, since our work is based on higher actuation stress and the actuation strain is limited, but we can think about designs like we can use multi-filament threads rather than monofilament or a film, and then we can twist together to get an addition of all these strains to get maybe a spring-like design to get a large actuation stress and stroke. And because the heat is generated within the polymeric film, which actually create these actuations within the polymeric film, so we can also generate the same process, the same phenomena using thermal energy instead of light. But this might be limited in certain applications. For example, in some of the electronics, if we need to use a localized actuations, we do not want to heat up all the systems. This might be limited, but there is a possibility. And we actually check using a DMA machine, a dynamic mechanical analyzer, and found out that the same actuation stress, similar kind of actuation stress, can also be attained using the thermal energy rather than the light energy. This is what I wanted to discuss, but if you have some time, I would like to discuss very briefly what I'm doing these days, and I'm really interested to talk about that. I will just take 5 more minutes. It is the development of light reversible motions in bilayer polymer metal composites. Since we found out that when we goes towards the film thickness, are we having a thermal gradient, the light is not either being used or being passed through the material without being used. So from that, we thought that we have to create a barrier from the later end of the film by using a reflective, maybe a fully reflective material, maybe like silver, maybe a reflective materials which can half absorb the light or half reflect, such as gold. and also a fully absorbing material such as carbon. And we also devise some patterns within the film so that we can generate different mechanical deformations like bending and twisting using different patterns of the coated films. So what we were expecting, if we create a metallic layer on the back end of the film, because the oriented polyethylene has a property of thermal contraction. That means when the heat is there, the polymer chains tend to contract. But the metal coating has a positive coefficient of thermal expansion. So upon heating, they will actually expand. So there will be a gradient of thermal expansion and contraction, which tend to create a bending or being a curve in the film. And what we are anticipating is that if the light tends to pass through the film, because of these metal coatings, such as silver, these light rays or photons will turn back into the light, thus increasing the actuation stress. So these are some of our references samples in which we have used 0% and 5% BZT, which were non-coated, and we illuminate that with the light. With the 5% and the non-coated, we hardly observe some kind of deformations within the film. This is purely because the film is very much stiffer, and also we are holding it from one end with the clamp. But if we use different patterns like 0 degree, 45 degree, and 90 degree, and illuminating it with the UV light, we experience some kind of deformations like twisting, like bending within the polymeric film. But again, these are not very promising results. What we were anticipating is something similar to liquid crystals, but again, we are comparing a soft polymer with a stiff polymer, which might not be possible. So we did observe some of the deformations, but these are not very much significant. What we can do, we can continue working on that, improving different parameters and see what happens. Or also we can also use rather using the metallic strip, because the metal is also very much stiff, restricting the polymer to get like mechanical deformation, bending, or stuff like that. We can use an isotropic film without being drawn. So putting it on the backside, joining them together and see what happened, because the difference between the negative coefficient thermal expansion and positive coefficient of thermal expansion of anisotropic and isotropic polymer films is like 15 to 20 times. This was another project I'm working on, creating a microporous yarn. Well, thank you very much. This is all about today's presentation. If you guys have any questions, please go ahead.
Thank you, Dr. Rehan. I have a question. It might be silly, but I was thinking to see, is this reversible or not? Like we saw that with light, it get bending, but how it gained their original position? Have you tested such kind of things or not?
Yeah, I would like to come back to slide. I'm sorry, I have to get back. Yeah, over here. So as you can see, as soon as we remove the light source, I turned it off like in a non-illuminating state, the process is reversible quite immediately, like very rapidly. So your question is why this happens. So we have to consider the polymer at a polymeric level, the chain-oriented chain level. So what polyethylene is consisting of? Polyethylene is consisting of a crystalline region and an amorphous region. So crystalline regions are, when we orient these polymers, the amorphous regions are being converted into crystalline regions. The crystallinity of the polymer is increasing. So, but at any point, if we are whether we are talking about high density polyethylene at a draw ratio of 15 probably, or ultra high molecular weight polyethylene at a draw ratio of 60 or 80. The only difference between these two is the concentration of crystalline and amorphous region. So crystallinity is being increased as soon as we increase the draw ratio. But at any point, the crystalline regions, the lamellies, are interconnected with the tautai molecules, which are elongated amorphous regions. So when we illuminate the polymers with the light and heat is generated, these tautai molecules, they tend to contract because of the negative thermal coefficient. And these are entropic-driven conformations. So when we remove the light source, because of the entropy, these tends to get back to their original state. Because the crystalline region on top and bottom, they are at their same position. So the entropy tends to get them back at their original position. As you can observe over here, the blue region representing the illumination state and white region representing the non-illuminating state. So it's just a matter of seconds when the response gets back to its original position, means the films are getting back to their normal position. But if we cross the alpha relaxation temperature, the films does not get back to their normal position because we are now crossing the elastic region of the films. The films, the tautai molecules get relaxed and they are like an amorphous region, which can go in either way. And or if we increase the temperature too much, the film might even melt.
Thank you.
Welcome.
Any more questions? Okay, well, if anyone has any more questions, I believe we can include Doctor's email in a YouTube description under the video. Is that okay?
Yeah, sure.
Yeah, well, thank you very much for this very interesting presentation. And I would also want to invite everyone for the next seminar, which is going to take place on the 12th of June. I believe it's going to be Laura Clark, so our print master. Thank you very much again.